and you go to the next step, and you become even larger. And so it means that you grow at a much faster pace. So next step, you become even larger. So this is what we call the exponential growth. You just grow so fast. So initially, some politicians said that COVID-19, we just only have 500 cases now, not piece of cake, totally controllable. But then if you don't do anything, it suddenly becomes 10,000. So exponential growth is really fast-paced growth. And initially, that exponential growth will dominate the whole dynamics because n is quite large. Then, in the later portion of the dynamics, the out rate dominates because we're talking about I squared, not I. So it will rapidly increase. But as you know, the maximum you can go with I is n. That means all the population are infected. And under that condition, the left term, the in rate Rn I becomes Rn squared, and the right term, the out rate, also becomes Rn squared. In that case, this whole thing becomes zero. It means that di over dt becomes zero. It reaches a steady state. So it does reach a steady state because there will be no further change, and under that condition, I will be n. That means all population will be infected. Well, I say for the third time, we are only trying to become a user of mathematics. We're not a creator of mathematics. So what we can do to find a solution is, well, it is actually solvable. You can do it. And I actually hope that you do try, but you actually don't have to because we can use our computers. So the one thing you can do is to go to a website, any website that does finds a solution for your equations. And there's one such site. It's called Wolfram Alpha. So just go to this website called wolframalpha.com, and you can plug in the equation. Note that I put x rather than I, because if I put I, Mathematica thinks that I is the imaginary number, so that we get to do the job. So I happen to use x, but it doesn't really matter. The name of the variable doesn't really matter. Anyway, you can just write down the equation, and then among all the things that you can consider with this equation, you actually think about the solution of this differential equation, and there you go. What you have is the logistic function. You can solve the same thing with any symbolic computation tools. One of them is Mathematica, but I'm not saying that Mathematica is the only solution only tool that you should use. It's just one of those available solutions. And there is an analytical differential equation solver called dsolve. So you put your equation into this dsolve function, and you just put a ordinary differential equation to solve, and then you also put the initial condition. And in this initial condition, I assume that initially there's only one patient, one infected, at time 0. And I let this equation solver, differential equation solver, to remember that we are solving it for I, and the variable I is dependent upon time t. And that's all we do, and it automatically finds a solution that looks just like the one that we saw before. And then you have to think about what this equation means. So initially, we just verify if it gives you the initial condition that we have already plugged in, which is I0 equals to 1. Just to verify, you put 0 to this equation solution, and because e to the power of 0 is 1, and you can quite easily get that this equation gives you n over n, which is 1. So this is verified. But if time goes to infinity, so you're now considering the condition. You're now considering what happens on the far end. Time goes to infinity to see if there's any steady state condition. And you only have to take the limit of these two functions. I don't even write limit in my classes normally, but then because this is an online course, I try to be a bit more formal. So we put this limit sign, and then thing about considering limit of that goes to infinity is that you cannot directly deal with infinity. And e to the power of infinity will be infinity, but how do you compare which infinity is larger infinity, right? So you just have to remove it by dividing it by e to the power of nRT. Then if you do that, you can remove this infinity, and then you do it to the denominator and the other side as well, and then on the far right, you can see that there are terms that are like -1 divided by e to the power of nRT, and this is certainly becoming 0, right? You're dividing infinity 1 by infinity, and it is 0, so no doubt about it. And n is also a constant, so if you divide n by infinity, it becomes 0 as well. So there you have it, you have n. So it just tells you that if the time goes to infinity, it becomes n. It means that the infected people will be eventually the whole population in this model. In reality, and I never reaches n due to immunity. So there are people who will recover from this pandemic. Upon recovery, even if a infected come into contact with him, he will no longer be able to transfer the disease to other people. So they become effectively a barrier to other naive or susceptible population. Also, it never reaches end because some of these pandemic is fatal. So some people will die. If people die, although they are infected, they no longer become able to transfer the disease. So you'd have to think about these considerations. If you get to think about this, in reality, n never becomes, I never becomes n. It becomes certain number lower than n itself, but that's something that we'll consider in a more sophisticated model called SIR. Now, I have uploaded this solution online, and I hope that you play with it. And if you play around, you will realize the same thing. But I consider certain numbers for your consideration. So if you look at this code, I put some parameters. First thing is that the n, the number of population, we only consider a small village composed of only 1,000 people. And let's say in this society, it is not very social society, perhaps. Those people meet only 2 people per day. So n equals to c is 2. And then we get to think about how many population, how many people are initially affected by the disease. And we assume that initially just one person carries the virus. And then you can calculate the rate of transfer of disease given these parameters, and it gives you the number 0.003996. And you can plot it using these parameters, and this is a graph. And in Mathematica, you can just simply use the plot function just to plot the whole thing. Sometimes it doesn't plot the whole range. So I put an option called plot range all. So please plot everything. Don't cut it arbitrarily. So that's the result you have. On the x-axis, you see time. Once again, time is arbitrary. But once you determine that C, the contact rate, is by day, then time t will be by day. So in this simulation, it composed of only 1,000 villagers, with one person meeting two people. Within only like 3 days, the whole population will be infected. Quite dramatic. But then you can plot the same thing using the log plot. So this is a bottom plot that you see. On the x-axis, you have the same linear scale of days of time. On the y-axis, you have a logarithmic presentation. And if you do present logarithmically, the exponential growth can be represented as a linear growth. This is quite useful if you want to guess the rate of change, because the slope tells you this rate. And in fact, if you search the internet, you get to, well, you don't have to search the internet. If you're doing any SNS, I think you have seen this kind of graph already. So this guy, Alessandro Strumia, he's a physicist, and he collected all the data that is available for free on the internet about COVID-19 cases, and he just plotted in the log scale. What he did, quite interestingly, is that he plotted after shifting the time series such that he plot from the time when the patient number reaches 200. So he's trying to adjust the x-axis, basically. And as we have seen earlier, initially, according to this model, initially the growth will be exponential. And the rate itself dependent upon the social conditions and so on, but most of the social structure is quite similar all around, and because of the scale-free structure, more important, more pertinent to this discussion is the nature of the virus. So it comes out that the rate is quite universal throughout the world. So as you can see, the data is from China, Germany, United Kingdom, South Korea, France, Sweden, Italy, Spain, Norway, so on and so forth. And all those countries have the same rate, exponential growth rate. There is a curious outlier people talk about, but let's ignore that for now. But it just proves the point that initially the growth is logarithmic and the growth rate is quite universal. So it's quite interesting. I mean, this is really simple equation, but it explains the phenomenon remarkably well. Now what you can do is you can think about what to do under this scenario. So once again, suppose the unit of time is day, and then you have to think about how many patients you will have per day. This is very important practically, because if you are running a society, there will be a certain number of patients that the medical system can take care of. So, for example, in your small town, you have a small clinic, and maybe you have 100 hospital beds, 200 hospital beds combined. Then you don't want to have more than 200 patients at a given time. So there's a need for control the rate of increase. It will eventually, according to this model,